Okay, hey everyone, welcome to the ISC seminar. It's my pleasure to introduce Professor Revzen. He's an associate professor at the University of Michigan in the Department of Electrical Engineering and Computer Science with an affiliation in the Ecology and Evolutionary Biology Department. He did his PhD at Berkeley in biology, studying neuromechanical control architectures for arthropods. And then he did his postdoc in the Nebraska lab at UPenn, so more robotics focused. Excited to hear about his work today, which is going to be in an application area that's really interesting for the lab. This kind of grander vision of in-situ manufacturing and deployment of robots. I had the privilege of being advised by Shad for my PhD thesis, so I'm really excited that he has an opportunity to see some of our work and share this work today with us. So, one final note, as is somewhat commonly the case for these seminars, this seminar is available outside the lab, so please keep any questions to open comment. So thank you, and without further ado, Eric.
Thank you for the introduction, Brian. And yeah, I think one of the best things I did is train Brian in my lab. This talk might be a tad disappointing in the sense that I'm not going to talk about the in-situ building of robots at all. What I'm going to talk about is all the work I've done to try and make that possible. So it's mostly a sales pitch for things we've done in the lab. I'm not going to give the technical details of how we did anything in the interest of actually reviewing a lot of the things. So what are the achievements? What am I actually trying to sell? Basically, these 8 things that we have looked at building robots quickly and with minimal tooling. We have looked at some methods for control that enable to do deadbeat control and smart controlling and replanning very cheaply. We've looked at several methods of damage recovery for robots, and we have made substantial progress in resolving a lot of the problems that we might have with multi-contact, in particular multi-legged robots, which has been my focus, and in modeling robots without actually knowing the physics of the interaction. Okay, so there will be sort of 3 parts to this talk. The first part, I'm going to give a little bit of the background, what my approach is, and sort of earlier work. So this all starts a long time ago. This starts in '99 with this book called The Case for Mars that is now pretty well known. And I was going through New York on the way back home to Israel, and there was a pile of these books in a bookstore. We used to have bookstores back in the day, and they were trying to get rid of these because these were hardcover books that no one cared about. This looked cool. I bought it for a friend of mine. I read it on the airplane, and it changed my life. Because I was in the tech world and a pretty senior position and bored out of my mind, and I thought, oh, this would be really cool to work on. But the main insight of this book was the Mars Direct plan, which was this idea of sending a robotic lander to Mars and launching it back by creating the fuel in situ from the Martian atmosphere. There are huge savings in fuel and cost for the lift vehicle because you don't need to lift the fuel from Earth. This was pretty shocking back then. Back then, the number quoted was 40 grams, $40 per gram launching to geo-orbit. Inflation adjusted for today, that would have been $75 per gram. That's not where we are now. Since then, a lot has happened. The 25th anniversary edition of that book is out. The second book by Revzen is out. A man you might have heard of by the name of Elon Musk founded a company called SpaceX because he was inspired by this idea. And we are now at $20 per gram to geo-orbit. So things are much better. And NASA and SpaceX are both building on this Mars Direct idea. And many players are considering in-situ resource utilization approaches. But the basic idea is still fundamentally the fact that it's really, really hard to send matter into space. And I think the part that's being missed there is not only is it hard to send matter into space, but there's a deeper logistic problem. And I'll get to that in a bit. But first, what I think we're also realizing is this is becoming a major geopolitical issue. So these are just news items from recently about the competition between US and China about Mars, the observation that whoever rules the moon has a huge strategic advantage can go back to Heinlein's classic, The Moon is a Harsh Mistress. If you haven't read it and you like sci-fi, you should. Remarkably prophetic, as many of Heinlein's books are. So the first thing I tried to think about was just think about defining what's the essence of the problem that's unique here. And I talked about that in a TEDx talk many years ago, but the idea is this notion of the unknown challenge mission profile. So it's thinking about the certain class of mission, which are really tricky because we don't know what we need to do in advance. And we're really limited in fuel, energy, mass, volume, parts, all the logistics that will enable us to adapt our systems to the need. And here are a bunch of missions that have that profile, but the essence of the definition of this, it's a mission that requires the execution of a set of tasks, each of which is tractable on its own, out of a collection of tasks that are intractable together. So obviously we can't do the things we can't do. But sometimes we could do the thing if we knew in advance what we needed to do. The problem is we don't know in advance what we need to do. The problem with the rovers going to Mars a few years ago, going next to this cliff face, which may have had evidence for life if the rovers could climb into the cliff and take a sample, but no one thought they'd need to climb a cliff sending it over to Mars. So we don't know, and we won't find out for decades. Would the mission planners be willing to sacrifice other scientific goals to climb into that cliff? Probably, if they had that choice. And this is the sort of problem, right? We know how to climb a cliff with a robot, but we don't know in advance which capabilities we'll need. And so how do you address this problem of not knowing the specific challenge in advance? Well, to the extent you can, you want to send bits and not bodies. You want to commit the physical form of your robot after you know the details of the tasks you want to perform. And one way to do that is to have a versatile body that can be reconfigured or synthesized in situ. Another advantage of doing that is that the more mass and volume you get from harvested resources, the more you save on launch capability, the more versatility you get, the more robots you can deploy. But you need a very, very different approach. And that approach is making every gram count, in part with the supervised autonomy, which you guys know very well how to do, but in part also with these questions: how do you get reliability and survivability of systems? How do you achieve graceful degradation? How can you use mechanical control instead of electronics? If we're going to fabricate a system out of materials that we harvest from the moon, we're not going to know them the way we know aluminum harvested here on Earth and prepared to a complicated industrial process. Right? The materials will be uncertain, their quality will be uncertain. So how can we be robust to extreme internal malfunctions, body variability, and environmental variability? And all of these are properties of animals. So if you think about it, biology does that all the time. The example I like giving is, you might not be aware of this, but the average human has about a ½ inch of leg length discrepancy. So you think your legs are the same length? They aren't. Most people's aren't. If you look at the people who do bipedal robot motion planning and you tell them that they're off by ½ inch of the length of the robot leg, they're going to have a bad day. Because we assume a lot of knowledge about our planet, about our controlled system, which biology doesn't assume. So my approach was a bio-inspired perspective, and let me talk a little bit about that. So animal locomotion is basically the model I've been looking at. This is the challenging environmental interaction problem. Animals move at all scales across a great variety of environment. And they do that robustly, and they do it with mechanical feedback that plays a big role, and they do it with a lot of modularity. And what do I mean by extreme robustness? Well, I hope nobody here is very squeamish about cockroaches. I spent my PhD working on cockroaches. Look at these two cockroaches. Actually, this is the same cockroach running on the terrain twice. Can you tell the difference between these two videos? Let me run that again. So in the bottom video, all the feet have been taken off. This is a bit horrible, but we're allowed to do that to arthropods. And no one really loves cockroaches, but imagine you had your car try to go across rough terrain, but you ripped off all the tires. How well would it move? There is no measurable change in the performance for the cockroach. This is the sort of robustness that biology achieves. And we would love to be able to achieve in robots, but we're really, really far from that. And I have dedicated most of my career to understanding how to do this better. So one of the sort of the reliability is modularity. I love the paper on the left from 2007. Someone actually went out into the field and measured how many legs do arthropods actually have. So you were taught that insects have 6 legs and crabs have 8 legs. But crabs in the wild usually have 7 legs or 6 legs because they sacrifice their legs to survive a bird attack, and then they regrow them. So this idea of a spare leg hypothesis, a more recent paper by Tanya Shea from Temple University shows the performance difference as the crabs lose legs, and shocker, there's almost none. Basically, they have spare legs, and that's great. Another really interesting result from the NS paper on the top right was manipulating the genes on shrimp to grow additional legs. It turns out that not only did they manage to get the shrimp to grow additional legs, but those legs got wired into the nervous system and worked just fine with the other legs in coordination. That's a level of modularity that we're not even remotely close to in robotics. Just slapping on an additional actuator on the robot and having the control system adapt to use that effectively. But it's obviously achievable with fairly simple computational infrastructure, because that's what arthropods have. So part of what's happening in animals, the control algorithm is not easy to understand. If you look at the toy car suspension on the left and the ostrich suspension on the right, it's pretty easy to understand the function of different components in the car suspension, because there's a part and it has a unique function, and that function is only in that part, and other parts can't compensate for the absence of that function. But if you look at the ostrich leg, which part here is shock absorbing, which part here is control, which part, each mechanical part is participating in multiple aspects of control. And the interaction between function and form is very complicated. And I have this obligation as a biologist to have this one slide every time I speak to engineers. Ryan looks sad because he's seen me talk through this slide a bajillion times. Biology doesn't optimize. The only thing it optimizes is Darwinian fitness, the number of viable offspring. So when you look at any specific function on an organism, you can't actually learn from it without talking to a biologist who understands the context of this organism very well, because evolution tinkers and co-ops existing features, and usually one feature of the organism does multiple things. And there are a lot of extraneous constraints on the design of organisms as engineered systems. For example, animals need to grow. Imagine designing a car that works from this size of the toy car to the size of the minivan as it grows. Would that change the design constraints you have to deal with? Spectacularly, but that happens to every arthropod. If you think about the direction evolution is taken, linkage, which is the phenomenon of which genes are next to each other on a chromosome, can completely bias the direction evolution takes, where two genes that are close to each other tend to move together into offspring. That's going to bias the evolutionary process to pick certain solutions versus other solutions, having nothing to do with any environmental factor. It's entirely within the genomic layout of the underlying species. And perhaps the most famous example that even Darwin knew about evolution doing things that don't make engineering sense, is that sometimes it's better to be sexy than to be successful in any mechanical sense. As for example, antlers show us, right? Antlers are a terrible idea, but they're a great way to show up, to show the ladies that you can get a lot of calcium each season, which means you're really good at getting food, which makes you really hot. So you need to really understand biology well in order to pull out ideas from biology. But I'll veer off of this to the last part and say, this is mostly work I did in my postdoc, except for the last bit. I did a bunch of work on trying to synthesize robots on the fly, and I was working in modular robotics lab with Mark Yen. We had this really cool paper where we actually synthesize a robot on the fly. So this is Foambot, this weird looking mothership robot on the left, deployed these little clusters. You see one of them sticking out here that can crawl across the ground. They lay themselves out on the ground, and then this robot sprays a body that connects them. And so we can decide, do we want to build a quadruped or do we want to build a snake? Or we build a few other things with this robot. The basic idea is we can decide the shape of the robot we want after we deploy our system. And there are a lot of challenges to do this, and we tried to do a Foambot too, which uses a much more rigid foam. You can see me standing on an inch-thick plate of that foam. We tried to build a quadcopter. We had everything sort of working. We had one go to build the quadcopter. It broke, and the students graduated, and that was the end of the project. So you've never seen Foambot 2. It's the robot that never happened. But we're that close to making a follow-up. But this is a very challenging problem, primarily because of issues of foam chemistry, as it turns out. But we also tried another approach. And that is, consider the usual sort of problem that soldiers have in the field. They want to take some equipment for, say, gathering intelligence with a flying vehicle or something that travels over water or something that travels over land. The classical solution is you have three different things. You have a plane, a boat, and a car. Now, you could think, oh, well, maybe I could have an amphibious car or a seaplane. Those are terrible. They're terrible as planes, they're terrible as boats, they're terrible as cars, and they're terrible as boats. The compromise is huge. But another approach is to have a single system that can be reconfigured into these three different functions. And that's what we did with Seal Pack. So this pack is about yay big. It fits easily within the backpack, and it can become this quadcopter, this pontoon boat, because we didn't have water sealed modules, and this car. So the same thing can be reconfigured in 5 minutes into these three forms. And the car is a good car, and the quadcopter is a good quadcopter, and the boat is an okay boat given that it's a pontoon boat. So they're actually pretty competitive in terms of their operational envelope in each of these domains. So it was another proof of this idea that committing to the shape of the robot in the field is something that's doable, and that the flexibility of our actuators and their software can make up for the difference. So these are the same motors functioning here as quadcopter motors, here as just wheels for a vehicle. And here, one of them is steering and the other is providing thrust. These are completely viable things to do. So that was exciting. And then I went on to start my work in Michigan and built this series of big ant robots. There's a manufacturing system called smart composite manufacturing that was used to make the RoboBee robots and the Roach robots in Berkeley. those were all either millimeter scale or centimeter scale robot. And what I set out to do in my lab is try and see whether I can get a manufacturing system that can be at the meter scale for robots, but still have minimal materials and tooling. And you see the different generations, but this started out as just an undergrad student project. So A is just a copy of the Roach robot chassis scaled up to meter. It can't even stand because structures don't scale nicely. By the time we reached the last robot, you see it's quite capable, but it is also still made out of two materials. The entire chassis cost us $20. It's made out of foam board plates, which are about $2 a sheet, and one roll of really fancy fiber tape to make the flexures and reinforcement. And just to prove the point, we've made these legs with a box cutter, and that works just fine. So you don't even need the laser cutter we used to cut the foam board to make this. So this entire family of design requires two materials, a plate material and flexure tensile material. And if we could generate those materials with these sorts of functions, say using in-situ resources on lunar mines, we could enable a whole family of designs, which we could then design on Earth, send the design information out, and fabricate in situ without sending more material. And just to give you a sense of what Big Ant can do, this is Big Ant taking a little walk. I think I won't, in the interest of time, I won't go through the whole video, but if you look up Big Ant on the wave field, that video is available online, and there's a follow-up video with a water-resistant version of Big Ant doing the same for the snow drifts, and actually doing better than humans, because it turns out that being a biped over snow drifts is really uncomfortable, but for hexapods, life is easy, and you don't fall over quite so easily. Okay, so we can make robots easily from very few materials, but the question is, can we control them, and how do we model what animals do in locomotion systems? So the approach that biomechanists have used for a long time is to use a hierarchy of models. We can use very abstract models, sometimes referred to as template models. These are very simplified models. Or you can use very anchored detailed models. This is someone actually sectioned this cockroach and rebuilt the model in atoms. Okay, so this is a precise model of an individual cockroach. And there are a lot of work on these. But I will also point out that all these systems these models are hybrid dynamical systems. They have collisions. And from a physics perspective, a collision is something that's fast and complicated, but we can predict the outcome. Okay, so there are places where we need these shortcuts because we want to avoid the complexity that rigid bodies don't actually exist, despite their convenience for us. And there are all these sorts of things like acoustic propagation, plastic deformation, surface interaction that we don't want to model. Let me ask you the following question. If you're running on rough terrain, do you need to see the ground to follow the ground? So the ground is going up and down. I want to move up and down with the ground as I'm running. Do I need to see the ground? The typical human answer is yes. Of course, I wouldn't be asking this if the answer weren't no in some interesting cases. So we're in domain A, we're in the air. Domain B is when we're on the ground, and there's an overlap between these domains, the area O, where we might hit the ground at any time, but we don't know where the ground is. It turns out there's a really easy way to hit our target S in domain B, which is to fake it till you make it. Pretend that you've already landed on the ground. Move your leg as if it's already on the ground. But then when you actually hit the ground, it won't matter. And that's a very general solution. It's not quite full measure because there's an orientation issue in the space there. So all I can say is, if the signs are right for that orientation, the entire volume of systems that you could have will admit this kind of solution. And if you're unfortunate, none of them will. But it's certainly a general thing. And we did that both with a spring-loaded inverted pendulum model here that's hopping along, or a vertical hopper where here the x-axis is time, and what you see is the ground is shifting up and down. The hopper is deadbeat tracking the ground, except it's not sensing the ground at all. It's just doing a carefully chosen trajectory for the toe that has the property that whenever it will actually hit the ground, it will make you bounce to the same height. And so this sort of inverse problem is actually solvable. And can give you deadbeat control. So that's sort of a warm-up to say a lot of things might be easier than you expect with legs, and that has been my experience so far in my career. Let's look at one important way of reducing systems. This is the formal way of thinking about those templates and anchors. The formal way to think about it is the template is some subset of states of the anchor, which is attracting. It's a reduced order dynamic that exists within this more complicated system, and its algebraic signature looks like this. But the important thing about templates is they govern what happens after the transients decay. So if you're talking about your plane doing the maneuver and the wings are vibrating some complicated way that relax pretty quickly, and then you know where the plane is going to end up, which is as if it was a rigid body if these really decay properly. So does this work? Can we do this? Well, the easiest way to do this is that the template is a one-dimensional loop. That's the simplest sort of persistent dynamic behavior we can have. Turns out that you can reduce a cockroach to an oscillator. That is a one-dimensional loop. And this is stuff I did in my thesis work. And so now that we think, okay, maybe this running animal, which is going to hit an obstacle in just a moment. There we go. You see that blur there is an obstacle that the cockroach is running over. It's on a transparent treadmill. If you think of the animal as an oscillator, the next thing to think about is, can we use this insight to think of this as a perturbed oscillator and use the perturbation models, which the guy by the name of Floquet showed us in the 19th century is actually a linear time varying system. It's an linear time periodic system, so time varying and periodic. You can reduce the response to perturbations to an LTP system. And when we did that for human running, we got much better prediction. So this is our prediction error starting at the moment of prediction to the future to 2 steps. Our full state prediction or our factor prediction both give very, very low error compared to dynamical models. And it's probably the best predictive model of human running today. If you wonder why does the prediction fail after 2 steps, there's a good reason for that. It turns out that human running is deadbeat after 2 steps. That is, all the information about your perturbation is gone after 2 steps because you fully recovered. So that's the prediction, right? Okay, so I showed you that phase reduction is useful. Let me now convince you that we can use that to achieve some interesting kinds of robustness. So one way to think about recovery then is, let's talk about a body that might suffer damage, so parts could break off or get stuck, but it still is fundamentally governed by the flow of mechanical energy. Right? Energy goes into various reservoirs and is exchanged between kinetic energy, potential energy, and elastic energy and actuators. So we built this really strange robot. It has these big sticks on it that enable us to measure the bending of these string lengths pretty accurately. So we can actually measure the energy flow in this robot as it's running along the floor. And it turns out that the vertical energy flows sort of look like this as a function of phase, and the fore-aft bending in this direction looks like this as a function of phase. So we store this. And then we ask our locomotion policy, which is a high dimensional object, to reconstruct the energy flow. So all we're trying to do is we're trying to reconstruct how energy was exchanged in the structure at a very global level. And these are basically just two energy reservoirs. So we don't have any details about the morphology of the robot, but we try and reconstruct the energy flows, and that optimization reconstructed our gate, reconstructed the ability to run. So basically, we relearned how to run by just reconstructing the internal energy flows, which we could potentially measure if we instrumented them internally, but we measured externally because that was just convenient for our experimental system. So, so that's one way to achieve robustness, and that paper has a bunch more interesting cases for that. There are many times where you can actually exploit the implicit function theorem to get the solutions in closed form and not even need to add that learning component that we use here. Let me ask you another question. And let's say I have some first order reference dynamics. So it's really easy to design first order systems, right? Usually we use gradient systems or gradient systems with an offset, and we can design a system that goes to a certain place or avoids a certain obstacle. So let's say we want a dynamic system that will follow a first order reference. And we want it to avoid complicated obstacles. So if it gets stuck in a cul-de-sac, it should back out and do these sorts of things. And we want to do this replanning on the fly. Normally we write a bunch of code, right? We want to detect that we're stuck. We then change to a different state. We backtrack. We do a whole bunch of planning. This is a system that's trying to go to the dotted line to the right. So this is this little puck here. It gets stuck, it bounces back, tries to go through here, gets stuck in this, backtracks out of this, misses this obstacle entirely, gets stuck in this obstacle, backtracks out, and eventually circles around. And it does this ODE. Okay, so the trajectory replanning here is happening by, instead of trying to force our system to the reference, our system has a combination of a hallucination of its first order reference, its own state, and a way of resolving the discrepancy between these two, which is just bounce back and to the left. The only knowledge it needs about the environment is an approximate notion of how big a scale makes sense for that bounce back. So it has one bit of information about the environment, which is what's the typical scale of obstacles I should deal with. And that's enough for this ODE to solve a problem that looks like it's being solved by a computational algorithm with a bunch of conditions and coding. So there's a lot more that can be packed into simple dynamics. And I expect, and there's some neuroscience suggesting that this sort of level of thinking is what's happening in a lot of arthropods. They're not doing a lot more than that. Let me talk now about what I think is one of our biggest wins, which is how to deal with multi-contact, multi-collision events. So there are a lot of types of hybrid dynamics out there. Let's talk about hybrid dynamics where we can have multiple hybrid events. In this case, this is leg 1 hitting the ground versus leg 2 hitting the ground. One kind of hybrid dynamic says which ODE we end up with depends entirely on the history. So there's one equation when happened to anything, one equation when the first leg hit, the third equation when the second leg hit after the first, and it's going to be a different equation if the second leg hits the first time and the first leg hits second. So it's complete history dependent, it's very general. If you have a lot of contacts that can happen, this grows combinatorially in a really painful way. The other approach people use often is you see people handling multiple contact with complementarity systems. And the baked-in assumption when you write equations with the methods of complementarity is that the effects of additional contact are additive. And you have an equation that adds a bunch of terms. Some of these terms have the little complementarity structure to them that enable them to model being in contact or not in contact, but the influence of these terms still has to be additive. We're talking about something that's in the middle between these two. So event selected systems, the equation of motion depends only on the subset of events that happen, but not on the order in which these events have happened. And I think this is a more realistic middle ground, because usually the collision itself is where the history effects happen, but after I have a contact established in the environment doesn't care which foot landed on the ground first. And so event selected systems, which is what we studied, are an interesting way to model that. And there's a bunch of formal structure there, but the basic picture is we have guard manifolds, that is conditions that have to change to our equations of motion, typically establishing or breaking contacts. Our system starts at some initial state, and event number 1 happens, and event number 2 happens, or event number 2 happens, and event number 1 happens. I'm sorry, I named them wrong compared to the numbers in the figure. But the point is, we're assuming that all events will happen. So this is what happens when a body relaxes into the ground and a bunch of contacts happen. It's what happens when I grab my cup and all my fingers will eventually hit the cup. I just don't know in which order. And it turns out that when you have a system like this, the trajectory that goes through the multi-contact event is not in general. The flow through the multi-contact event is not in general smooth. It doesn't have a conventional derivative. But what we showed in this paper is that it has a piecewise differentiable structure. It has something that's a little bit like a derivative. It's called a Boulegan derivative or a Boulegan differential. And after showing that, that shows us how to do first order approximations and iterative improvement. And what we showed in a recent paper is that there is an easy way to build an equivalent system, a system that will have the same local sensitivity to perturbations, but that really simple system we can use to compute very quickly the multi-contact dynamics. What do I mean when I say very quickly? So imagine I have this stool, it's bouncing on the ground, which has some spring damper behavior. So without the damping, this system would just be continuous, because the spring hitting the ground just builds force gradually, the system's continuous, everything's fine. But because of the dampers, the velocity with which we hit the ground matters, and actually have a different force depending which velocity we have. So if we take this two-legged chair bouncing on a spring damper, we get a speed of about 1400 compared to a conventional ODE integrator detecting events and then going through the events. You go up to a three-legged chair bouncing, we got a 43,000 times improvement on the execution time. So just remarkable, right? This is basically turning the multi-contact problem to a conventional smooth flow problem in terms of the execution time. And in case you're hoping that this would be useful for you, we're now working on the general purpose integrator. And if you want to play with it and beta test it, talk to me. My Revzen is debugging it as we speak, I hope. So that was a really nice success in enabling us to work with multi-linked systems. But we had another really interesting success, and this is primarily Brian's work during his PhD, and it's using the idea of symmetry reduction. So the other way we can simplify complicated physics is by using the underlying symmetry of the physics. The basic symmetry of motion is that the laws of physics don't depend on our frame of reference, and therefore we can actually factor out the state into two parts: a body frame representation and a shape. The shape is the quotient of the state body frame symmetry. And then we can write the body frame velocity in terms of shape and shape velocity. And the body frame really becomes an output. The body frame velocity becomes an output. This is what you're used to in just writing equations in body coordinates, but it's sort of a very formal mathematical underpinning of it. You end up with a group momentum, which is what carries you through the symmetry. It's a generalization of Noether's theorem. And this is all formalized in a field called geometric mechanics. And in this equation called the reconstruction equation, it says that our body velocity depends on our shape in the following way. There's a nonlinear function of shape that multiplies linearly the shape velocity, and that contributes to velocity. And then there's a frozen inertia tensor that depends on shape that carries the momentum into the velocity. And this is a very, very general result. That is, for any simple Lagrangian that's equivariant, this construction works. But most of my work has been on the case where this momentum decays quickly and you can throw away this term. And so now we have a really simple equation of motion that is linear in the velocities and nonlinear in the shape. And so Brian did this great work with me of let's try and estimate that connection. But instead of sampling exhaustively the entire state space, we can sample only in the vicinity of the gate. As the dimension goes up, the sample efficiency gains become huge because we're basically sampling a one-dimensional piece of a higher dimensional space. And so you get a really big win. Why is this good? Because often we don't know the physics of the system we're working on. And this is especially relevant in the context of space exploration, where we literally have no opportunity to do all the tests we would want to do to understand the physics that underlie the interaction with our substrate. We can simulate, we can try and build out these models, but we can't even do the experiments in the lower gravity here on Earth. It's just really, really difficult. And if we're trying to look at gates, which are high-dimensional policies or changing the shape, if we tried to do exhaustive sampling, we'd break the robot before we were done. And so our approach is build a local model of the physics using a few experiments, then simulate the gate gradient against our local model, which is valid because it's experimentally derived in this neighborhood, and do a step in that space. And the math sort of looks like this. We take our connection, split it into dependence, split our shape into a part that moves along the cycle and a part that's perturbed off the cycle. So we just do this substitution here. We do a first order Taylor approximation of A. We split up the terms and we end up with a linear regression. So it's the world's simplest learning algorithm is used here. It's called least squares regression. It turns out it works really well. This is a simulated example of the swimming gate for a snake. But I think more interesting is seeing this working on a real robot and seeing how quickly this robot learns how to move. So this is literally all the trials in the training process. It started out with a completely ineffective motion. And what you see is by trial 7, we already have something that's sort of noticeably a wiggling gate. By trial 8, it's going pretty well, but turning a bit too much. And by trial 9, it's going fast and turning less. In trial 10, we have what you'd hope for. So this is 20 minutes for a 5-DOF system. Learning how to move from scratch, not knowing anything about the physics, except that it will be governed by a connection. So if you have a system that is not going to build up momentum, this can learn how to move it way, way faster than a conventional machine learning algorithm would. Brian also showed this lovely result that we can do this with soft robots. So here we do the same thing, except we only actuated the black points on these structures. The red points are passive. And it turns out one way to think about this if you're a machine learning person is that These are really, really good linearizing observables for the underlying dynamics. So in general, the dynamics of wiggling a snake from the end by actuating the joints is very nonlinear. But with some physical insight, you can get a bunch of observables that actually make the dynamic linear in those observable and therefore easy to learn. And so we can learn how to make this 9-link swimmer swim based on actuating only 2 joints at one end. But this gets better because really, if we want to navigate an environment, we don't actually need to get one gate. We just need to get a family of gates that can get us anywhere we want in any orientation we want, right? We need a family of maneuvers or tools that can get us everywhere we want. And so we formulated this idea of, let's say we have just 2 primitive elements to use, these 2 red in motion, but we can sequence them. So we can do 1 and then 2, or 1 and then 1, and that gets us to different places. Well, now we can optimize jointly on these 2 maneuvers to get good coverage of the space of possible rigid body motions. And using that approach, Brian did this on this robot that just has a bunch of sticks that he collected because he was frustrated with people always assuming that he had models of his robot, and no one in their right mind would assume that you have a model for this robot. So that sort of proved the point. But the interesting thing is these libraries now allow us to recover from failure. So here we're optimizing the library. So we're getting pretty good coverage. These worms end up in a lot of positions and orientations, and then we're breaking one of the joints. And now they're no longer successful, but they learn pretty quickly how to reach that space again. So what you're looking at here in terms of our loss function is we train our systems and they reduce the loss pretty quickly, and then we break them and they recover from the break really quickly, even faster than they were learning the first time. So what we're talking about is the ability to recover full mobility in your terrain, even though you've broken part of your system. And we do that by not being too big-headed about trying to recover exactly the motion we had before. Instead, we're actually optimizing for what we care about, which is the ability to get anywhere in our terrain in any orientation. And that relaxation of the optimization problem lets us do a much better job. Okay, I need to finish on the hour. Yeah, okay, so I'll go a little bit faster through the remainder. But we're doing pretty well, I think. So the last bit I want to talk about is this, the one case where I had in my career to tell my students we did too well, now we're in trouble. Because we had these connection-based models, they look pretty good. And so I said, okay, let's build a toy model and see if we can derive these from first principles. So our toy model is just a bunch of springs on a plate, contacting the ground. There's a friction. Turns out you can't get a connection type model out of this because Coulomb friction is nonlinear in a really annoying way. So you can't get that to work. So you do what physicists sometimes do, you screw up the math to get the right shape, even though there's no justification to do that, sometimes called an ansatz. What we did was just remove the hat from V and replace it with an arrow. That is, the friction force is not proportional to the magnitude of velocity as well, and not just the direction of velocity. Why? Because it makes the algebra work out. Except that also made our results work really well. So this is the first robot we tried it on, model versus observation. Then we tried another robot. Then this was too good, so we got colleagues to send this data from their robot. And now we knew we were really in trouble because we have the wrong physics and the right answer, and that's not a good day for an academic. So we tried to do better. We added a way to find the contacts with including pitch and roll. So using a small angle approximation, it turns out that which legs are in contact is just a linear partition of space. And so you can use the following very naive algorithm to figure out having contact. It's basically a rapid simulation of how the robot would bounce between its legs as it's equilibrating. We start at some point, we solve for force balance, it's way out here, past the transition into a different contact state. So we project to this contact state, solve, it's way out here, past the transition to a new contact state. So we project to the transition. Now we solve and we ended up in the interior. So that's a realistic solution. That's very, very rapid. It's just a series of projections. So we can quickly solve for our contact state. Now we have our normal forces. We build that into our model and we do our simulation. And we get really nice results. I'll show the quality of the results in just a sec, but we also try to compare how fast is this algorithm compared to the Joko to make the comparison fair. Since we wrote a hacky version in Python and the Joko is optimized C++, we normalize both comparisons to the rate with which that simulator was running a three-legged robot. So it's a disk with three legs, it's jiggling around. We're simulating it with both the simulators. That's our baseline cost. Now we add legs and we compare how the Joko execution time scales with how ours scales. You notice something interesting. We're almost independent of the number of legs. So we can do a simulation with 30 legs, only 1.5 times more slowly than the 3 legs. So any objection you may have had to using multi-legged platforms and not knowing how they slip on the ground should be removed, especially when you look at the results. So because we were concerned that we might have the physics wrong, we actually built a robot that can measure the ground contact forces. This is a really tough problem. I won't go into all of what happens there, but just show red are our various measured properties. Purple is what you get from a Coulomb force simulation. Blue is what you get from our simulation that has the wrong force model. You notice that we're pretty close to Coulomb and we're both wrong in sort of the same way. Except we execute hundreds of times faster because we don't need to solve this change in contact state problem. We get pretty good prediction of motion. This is that same robot you saw there. That figure is broken, but this is an 8-legged robot with bouncy legs. We also get pretty good predictions. And so we put a gate for a robot that's intentionally designed to cause a lot of slipping to make sure that we're really stressing the part of the physics that people think is hard to model. And we get the same sort of result where our prediction is pretty close to the Coulomb friction prediction for all the traction forces, but it's done much faster and much more simply. And so I'll come back right to the end and say, here are a bunch of cool things we did that could enable you to build robots from low quality materials, not knowing what the physics are like, not requiring electronics to stabilize them, and have them recover from damage and go around obstacles with minimal computational work. And I'm happy to help improve the TRL on all of these, because these are just academic papers. I'm an academic, but you guys are closer to the real use of these. So yeah, with that, I'd like to also credit all the many people who have contributed to this project, these projects. Yeah, thank you.
Great, thanks, Shai. We have 4 minutes, so have time for a handful of questions.
Yeah, I had a quick question about the the plots where you had the energy, the elastic energy stored in like the roll direction and the fore aft direction.
Yeah,
You said that you were able to take those energy plots and then recover the gates without any prior knowledge of the morphology.
yeah.
Does that approach kind of work for if you took, like you took these trajectories of the energy, could you recover gates for different morphologies? Like you could take a similar like fore aft motion and then map that onto different types.
Give me a grad student year and I'll test that. Just didn't get around to it. That is the obvious question. I agree, but we just didn't get around to it. Yeah.
Okay, thank you.
Yeah, I will say this in George's thesis, he explains this a bit better. What I was trying to do with this is conceptualize what sort of constraints we actually care about for performing a task, while also making the sort of local learnability of policies really good. Right? Because it's very hard to update an indirect outcome of a policy that only happens through the integration with the body dynamics of the environment. But if you can give some hints that are local to push your policy in the right direction, learning policies happens much faster and much more efficiently. And so one way to do that is to try and think, what are the hints about the policy that I can have that will persist through damage? So no matter how many legs the robot has, it still has a total elastic energy. It still has a total potential energy. It still has a total kinetic energy. We can compute those, we can estimate those through a variety of forms of damage. And so those hints will persist through the faults. And so they can help us recover from the failure. And that intuition, I think, extends way beyond this work. And it's some of the mathematical tooling for doing that well is articulated in George's thesis. But, this is just a corner of it.
Maybe returning to the motivating problem, the clip on Mars. Kind of given some of the progress here, we think it's kind of like the next big technical, we're
I think we have two big gaps. One is that no one seems to be thinking about modularity in field deployable systems. The people who work on modularity in robotics are sort of this fringe contingent. And the people who work on field robotics are working very hard on fancy, expensive algorithms and sensors that have more and more customization in them. And so they lose the robustness that comes with modularity. And the real problem is the logistic tail, right? On Earth, no one knows how to make a pencil. No one person knows how to make a pencil, because there's so much technical knowledge in all the various parts. This is a plastic pencil. This is really hard, but even a wood pencil with a graphite insert requires more technical knowledge than an individual person has, even though it's a 2,000-year-old technology. If you're out on another planet, you don't have any of that logistic base. You don't have any of that tail to fill in the gaps when things break, to adapt your design. So you need to think about modularity, because modularity allows you to replace parts that fail. It allows you to be much more adaptive. And the insight that led us to PhoneBot was that Mark Young was really one of the first people working on modular robots. Did a lot of great work on modular robots. And when I was working with Mark, we realized that the problem is modules make really terrible bodies. People were talking about these reconfigurable modular systems, but imagine having your leg made out of a bunch of motors that are turned off. That doesn't seem very efficient. It's very expensive. It's a very heavy leg. It would make a lot more sense to make your leg out of some hollow tube of stiff material. So really, you need this balance of complexity in the modules with a bunch of material around the modules that's easy to manufacture and has good structural properties, but your demands out of that material are a lot lower. And that gives the potential to send to the moon or Mars a little bit of electronics and build a body around these electronics and be able to switch that body when you discover new needs or when things break. But the disadvantage is now, how do you control that? You have no model. How do you build systems that are robust and reliable for the mission while not having a good understanding of the material properties of your own body and of the environment? And so that's what I've been trying to explore primarily through biologically inspired ideas. And I know I haven't spoken about what are the various biological intuitions that led us down the tracks here, because I was already short in time, but I'm happy to fill in those gaps. Almost every idea here has its roots in something we know about how animals do things.
Cool. Well, thank you, Shai. Thanks everyone for attending today. That concludes the seminar. Let's thank the speaker one last time.